Okay, so it's 2 o'clock. It's my great pleasure to welcome you back to the Topological Matter Conference. We are now going toward the afternoon session, and it's my great pleasure to introduce our next speaker. It's Kirsten von Bergmann from the University of Hamburg, and she is an expert in scanning probes and spintronics. And she will address in her talk spin textures on the atomic scale. So Kirsten, we are very much looking forward to your presentation. Please go ahead.
Thank you, Tobias, for the nice introduction. Welcome to my talk. I would like to thank the organizers of the conference for setting up this nice program and for giving me the opportunity to share with you some of our recent results on atomic scale spin textures. So first, I would like to introduce what are the ingredients to actually get atomic scale magnetic structures. So obviously, usually we have this magnetic exchange interaction, and to get atomic scale magnetic states, it is sometimes favorable to have an antiferromagnetic interaction. Then, because we're talking about thin films and interfaces, usually we have some anti-symmetric exchange interaction or Janoshinsky-Moriya interaction, which sort of has the lowest energy once the spins are canted at 90 degrees, and then the sign of this prefactor D determines whether they would prefer to be at plus or minus 90 degree. And in addition, geometric frustration can help to get complex atomic scale magnetic order. And with geometric frustration, I mean that on a hexagonal atomic lattice, an antiferromagnetic nearest neighbor interaction must be frustrated because it cannot be anti-parallel to all of the 6 nearest neighbors. So other ways to lower the energy have to be found, and usually that's a compromise between different things. Also, exchange frustration can lead to canting of spin structures, giving rise to magnetic states on the atomic scale. So in this example here, we're looking at this central spin, and if we have a ferromagnetic nearest neighbor interaction, but an antiferromagnetic next nearest neighbor interaction, again, we have a frustrated system. And for example, this can be a driving force for spin spiral formation, which can then, depending on the ratio of the different interactions, lead to nanoscale or atomic scale spin spirals. And then there's another important thing, and this will be a central topic of this talk. It will be the higher order interactions, which can actually play a decisive role in atomic scale magnetic state formation. So they are either called higher order interactions or multi-spin interactions, and in particular, we're looking at 4-spin interactions where the exchange is mediated by a hopping between 4 spins. So it's not just a pairwise exchange like the isotropic Heisenberg exchange, but it's the next highest order of the exchange interaction. And this hopping between 4 spins can be attributed to a 2-side interaction or a 3-side interaction, or the hopping between 4 different magnetic moments. So this would be the 4-spin, 4-side interaction, and so on. And the details about these interactions you can find, for example, in this recent reference, where also now this 3-side interaction has been included. Now, what kind of magnetic states are we looking at here? So if we look at an antiferromagnetic interaction on a hexagonal lattice, then the ground state of the nearest neighbor antiferromagnetic interaction is the nil state. So all angles between nearest neighbor moments have 120 degrees. And this is then the magnetic ground state you will get. It has 3 atoms in the unit cell and always 120 degrees. Now, if you have frustrated exchange, so a competition between an antiferromagnetic nearest and an antiferromagnetic next nearest neighbor exchange, the ground state will be a rowwise antiferromagnetic state as depicted here. So you have these rows of parallel magnetic moment, and then the direction alternates from row to row. So it's also an antiferromagnet. And these states can be described by Q vectors in the Brion zone. So at the gamma bar point, you always have the ferromagnetic state. And then if you move to the K point, you go to the Néel state, 120 degrees, that's depicted here. And then if you continue to go to the M state, you have 180 degrees between the rows. And now you can already see that there's, of course, in one Brion zone, 3 different M states. So you can have rotational domains of this rowwise antiferromagnetic state. Now I want to come to the effect of the higher order interactions. This is a superposition of these 3 single Q states. And you can see that now it's a fully 3-dimensional non-collinear magnetic state. And this is the unit cell. It has 4 atoms in the unit cell, and nearest neighbor angles have the tetrahedron angle of 109 point something degrees. And if you do not consider higher order interactions, the single Q state and this perfect triple Q state, they have the same energy. And they are degenerate. So in a system without higher order interactions, these states would coexist. Now, if you have higher order interactions, one of those states is favored, either the rowwise antiferromagnetic state or the superposition state. And that just depends on the sign of the higher order interactions. And so this is the one of the few perfect states you can get by a pure superposition of the states, and the size of the magnetic moments is constant in this superposition state. In experiments, one has also seen the impact of higher order interactions, not in this system where it was predicted for, because this cannot be prepared experimentally due to intermixing. However, other systems have been found in experiments that show, for example, here this 2-dimensional magnetic structure in 0 magnetic field. And this 2-dimensionality of the spin structure is a signature of an impact of the higher order interactions, because it couples uniaxial spin spirals to form these 2-dimensional magnetic states. So this is found in an iron monolayer on iridium 111, and it's basically a nanospermian lattice, and the role of the higher order interactions has been confirmed in detail by DFT calculations in this reference here. And the magnetic state is something similar to what is depicted here. Now, every sphere and arrow corresponds to 1 magnetic moment. So you can see this is really an atomic scale non-collinear magnetic state. And this is what we're interested in. And I will show you what we can learn from these higher order interactions. Here's another example in the manganese double layer. So in total, you have an antiferromagnetic interaction. You have these rows of nearly parallel magnetic atoms, but then on top they do this spiral here. So this is a conical spiral, which is induced by the higher order interactions. And then 2 more examples, experimental examples, where I just show the spin structure here. So again, it's an iron monolayer now. And one sees that here one has an up, up, down, down state. So a double rowwise antiferromagnetic state. In this case here, the spins are slightly canted due to a competition of the higher order exchange, which favors this collinear structure, and the Jalushinsky-Maria interaction, which leads to such a canting. So this has been in the focus recently, not only as effect for ground state formation, but also regarding transport properties in materials. So there's many theoretical works that look at these kind of states and make predictions about topology in transport and so on. For example, also it has been shown that higher order interactions can stabilize skyrmions against collapse. So this is an evolving field. And the question is, how can we contribute from experiments? And how can we actually identify these kind of spin structures? And we use our method of spin-polarized scanning tunneling microscopy to investigate such atomic scale non-collinear magnetic order. So basically, we're using the TMR effect, the tunnel magnetoresistance, in STM geometry. So we have a magnetic tip, we have an insulating barrier, and we have a second magnetic electrode. Now, depending on whether tip and sample magnetization are parallel or anti-parallel, we draw a smaller or a larger tunnel current, and thus we can basically study magnetism down to the atomic scale. We usually do this at low temperature in model type systems, and all the measurements I will be showing here are measured in pseudomorphic films that are very clean, and the measurement temperature is on the order of 4 or 8 Kelvin. And all our samples and tips are prepared in situ in our ultra-high vacuum system, and this is also where they are studied. Now, this is the first system I would like to talk about. It's a manganese monolayer on rhenium-001, and we can stabilize the manganese monolayer both in an FCC stacking, which is the dominant one, or in an HCP stacking, which can be stabilized here by some addition of cobalt at the stack edge. So both these layers are perfectly hexagonal. They just sit in slightly different absorption sites. And now we want to look at the magnetic states that they have. So the dominant FCC stacking looks like this when we do SP, STM measurements. We see these stripes here, and we find that the stripes run along the close packed row, and that we see every other atomic row as a maximum, which means this is consistent with a rowwise antiferromagnetic state, which surprisingly had not been observed in the transition metal monolayer before. And we see that it occurs in these 3 rotational domains. And because they have different magnetic amplitude, we can conclude that our tip magnetization must be somewhat in this direction, and that the spins on the sample are dominantly in plane. What we also observe is that each rotational domain has the same contrast also in different areas. And this means that the spins couple to the antiferromagnetic rows. What I mean is that we have either this state or this state, and they do not coexist. Otherwise, it would not be in agreement with the experiment. So you might say, well, of course, you have either this one or this one. But then it's not so easy to actually find out which energy would make a difference between these two. For example, the isotropic Heisenberg exchange wouldn't know the difference. But for example, if you look at the dipole-dipole interaction, you see that this state is favored over this one by 0.14 millieV per manganese atom. So actually the dipole-dipole interaction can have an impact on the details of the ground state of an antiferromagnet. And there's another interaction that can actually differentiate between these two, and that's related to spin-orbit coupling. So if you do TFT calculations, including spin orbit coupling, you calculate the energies of these different states. So this state is displayed here. You see that there's also an energy difference, and this must be due to the anisotropic symmetric exchange interaction. Also favors this state for this particular material. Now, of course, we also want to look at the other stacking of this perfect hexagonal manganese monolayer, and we find something very different. We don't see the stripes as before, but we see this hexagonal dot structure. And if we analyze it, we find that it is a P2x2 structure. So this is some kind of atomic resolution image, it's manipulation imaging, and it very clearly shows the superstructure. And this is in agreement with the 3Q state, which also hadn't been observed before. That is the state that I'd shown in the introduction. The superposition of the 3 rotational domains of the rowwise antiferromagnetic state, which can be favored by higher order interactions. What we also see is that the pattern, it looks slightly different in different sample areas, suggesting that there must be rotational domains of this state. So if we look at this triple Q state like this one, you can realize that in a monolayer film, you don't have rotational domains of this state. But then you can also twist your 3Q state to have a different orientation relative to the film plane, for example, this one, and then you can immediately see that you will have rotational domains. So how can we check this experimentally? Well, if we take a tip that's magnetized perpendicular to the film plane, then we expect to see these different contrasts for these different structures. For now, we don't know what would make an energy difference between these structures, but there's some ideas where this can come from in this preprint here. And from the experiments, we can just make an experiment with this kind of tip and this kind of tip and see what we get as a magnetic contrast. So to realize this experimentally, we use a thin iron film on our tip and then apply an external magnetic field to either align the tip magnetization in this direction or in this direction. And we expect that the sample does not react to the external magnetic field. So this is what we then find. This is our hexagonal manganese monolayer here. So we see this area here. There's a zoom in, so we see this hexagonal pattern. And in a different area of the sample, it looks slightly different, but it does look like the simulations we had done before for this particular rotation of the 3Q state. And if we now invert the external magnetic field to change the tip magnetization, we see that the pattern does not change, except that we get a phase shift for the position here, as was expected for this kind of 3Q state. So we believe this is the state that we have here in our experiments. Now, this is maybe a bit of a fun fact, but if you look at the topological charge of this 4-atom unit cell here, and you calculate it the way we always do it, we find that within 1 unit cell, the topological charge is 2. So initially I thought, well, this might be the smallest skyrmion you could think of, a tetrahedron, but then it is something different topologically. So I don't know what this really implies, so it might be important for transport experiments. As I said in the introduction, there's a lot of interest in this sort of structure regarding transport. So for now, it is just a fun fact now that we don't see any effect on the physics yet. Now, this is an overview of this manganese monolayer. So here in the HCP stacking, you find the 3Q state, then you have a structural dislocation line here, and go to the FCC stacking where you always see this rowwise antiferromagnetic state. And then you see that you have these boundaries here between the rotational domains. And this is something I would like to discuss in the following. Now, if we have a rowwise antiferromagnetic state, first we can, for example, have such a phased domain wall where the rows on two sides of this wall point in opposite direction. So it's phase shifted. We don't observe them very often. What we rather observe is boundaries between these three possible rotational domains. And in this case, we can, for example, see the wall connecting these two rotational domains, and then there's an angle of 60 degrees between the quantization axes of these two adjacent rotational domains. Or we can have a wall in this direction, which is very symmetric, but then the quantization axes have an angle of 120 degrees between them. So these are somewhat orientational domain walls, and we want to study them in a little bit more detail. So you could imagine that as you go across such a domain wall, you just have a coherent rotation of the spins, and that's how you connect the two rotational domains as you would have that in a ferromagnet, and that's not the case. So here are images of a part of a 60-degree domain wall and a part of a 120-degree domain wall. And you can already see that it's not a smooth transition. In particular, here you see that some substructure evolves in this wall here. And this wall has this funny shape because we've added some cobalt atoms on top of the surface to pin the wall, so it can make these funny shapes. And here is another sample area where we actually have these in-layer defects or sub-layer defects, which actually hold the wall apart. So they widen the wall, and we can easily see and analyze the interior of the wall within this particular wall. And what we see is a P2 by 2 superstructure. And you already know that this has 4 atoms in the unit cell, and it could resemble a superposition state. And now that we have 2 rowwise states that sort of connect, we propose that this could be a 2Q state, as depicted here by these arrows. Definitely, we don't have a coherent rotation of the sublattices. So now to understand this in more detail, we take a minimal model of a Hamiltonian. So we have the J1 and J2 that give rise to the rowwise antiferromagnetic state. We have an easy plane axis. We need the anisotropic symmetric exchange to couple the rows to the lattice. And then we take this higher order interaction term, which favors the rowwise state over the 3Q and also the 2Q state, to have the rowwise as the magnetic ground state. And then we set up these 2 rotational domains and do spin dynamics simulations to let the details of the wall evolve. And this is the spin structure that we find for the 120-degree wall and for the 60-degree wall. And in particular here, this one is a little bit wider. You can see the resemblance with the 2Q state. So indeed, within our model here, the 2 rotational domains merge to make a 2Q state in their center. And now if you increase the higher order interaction parameter, you see that the walls shrink. And if you stare at these circles long enough, you can actually come up with an analytical formula for the width and the energy of these antiferromagnetic walls. And you see that now not the anisotropy is a decisive factor here, but the higher order interaction parameter determines the width and the energy of these antiferromagnetic domains. Now, this is not unique for hexagonal monolayers, but also in a square type, square lattice antiferromagnet, you can have such sort of things. In particular, in this P2x1 antiferromagnetic state, you can have this 2Q structure here. And again, you get it in a competition of the different J's. And if we set up a simulation, indeed, we see these superposition walls also in the square lattice antiferromagnet. So now these were very simple, straightforward antiferromagnetic systems, but we wanted to look at more complex things as well. So we have this complex nanoskirmion lattice in the iron monolayer on iridium, which is driven by higher order interactions. And for an iron monolayer on rhenium, we just have this rather boring Neal state. So now we want to see what happens if we transition between these two. So we slip more and more iridium layers in between the iron and the rhenium. So these are the states we studied experimentally. We found that this still has the Neal state, this one also, and also if we put 4 layers of iridium under the iron monolayer, it still has the Neal state. So iridium and rhenium, they have a lattice mismatch of only 2%. So there's basically no strain, and all this is pseudomorphic. So still the iron knows it's not iridium 111 as here, it's something different. However, if we have only these 3 layers of iridium, we again get a nanoskirmion lattice with roughly 9 atoms in the unit cell, and also it is square, similar to the one on iridium. So this is definitely something interesting. We get these 3 rotational domains of this lattice. Now, we know if we put palladium on top of this iron, we get a spin spiral in the skirmion lattice, an external magnetic field. So what happens if we put palladium on top of this? Let's see. So actually in both cases now, we also get spin spirals with a very similar length scale as directly on iridium. So here you see the spin spirals, all the blue parts are the palladium iron bits. If we apply an external magnetic field, these rings indicate that you have skyrmions here. And also then when we remove the external magnetic field, these sort of irregular spin spirals with some loopholes here remain. So we can conclude that the iridium is not equal to iridium. It depends on the thickness that you have, what you really get. So the system is very sensitive, but also one can always get interesting magnetic states, and one can get nanoscale magnetic skyrmions also in remnants on this rhenium, which is actually a superconductor at 1.7 Kelvin, but we did our measurements above TC. But still, this could be an interesting system to study also below TC. Now, I will run through the system where we transition between iron on rhodium and iron on iridium. So on iron on rhodium, it has been shown that it has an up, down, down state in the group of Matthias Bode and Würzburg. And actually, the stacking also plays a role for the magnetic state. You see here in FCC iron, we have a 15-atom square nanoskirmion lattice, whereas in the other stacking of iron, it's a 12-atom hexagonal nanoskirmion lattice. So we investigated capping the iron with rhodium, and again, we've seen that there's higher order interactions that govern the state. So now we've studied these systems here where we put the iron on rhodium with different backbone, basically. Now, looking at it, we see that in one stacking, we can get stripes. In the other stacking, we get a hexagonal state. Again, hexagonal shows that higher order interactions likely play a role. if we apply a magnetic field, we see changes in this hexagonal magnetic state, implying that there's a net magnetic moment. And looking at the details and atomic resolution images, we can come up with this kind of magnetic ground state for one of the stackings and this one for the other one. So this one is reminiscent of a skyrmion lattice with about 27 atoms per skyrmion. Now, I told you we also looked at thicker rhodium layers and the iron on top. Now here, this is one of the stackings, and we see these stripes and rotational domains, and it appears very similar as the up-up-down-down state that was studied previously. So we think this is an up-up-down-down state, whereas in the other stacking, again, we see a hexagonal state, likely due to higher order interactions. And we see that it's commensurate and can occur in slightly different tilts. We have this atomic resolution image and can derive this spin structure here, which is somehow canted by some magic angle. So here we have 19 atoms per skyrmion now. And with this, I come to the conclusions that higher order interactions are important on the atomic scale, and they really give rise to very interesting magnetic states, and changing only details like layer thickness or stacking can have a large impact on the details of the magnetic states. And I think with this, I will just conclude, not before thanking my collaborators. André Kubecka was a key player in all this work, and Jonas Friedmann. We're all in the group of Roland Wiesendanger, and Stefan Heinze was a big theory support, and we get funding from the Deutsche Forschungsgemeinschaft in these two projects. Thank you very much. Looking forward to your questions.
So thank you very much, Kirsten, for sharing these exciting results, also for being extremely punctual in time. We have now time for questions, and there is a raised hand. Just let me just check it. Ah, yeah, here's one raised hand. So the person with the raised hand, yeah, Yin Chuan, you please go ahead, ask your question orally. I try to unmute you. Sergio, can you help me, please? Yeah? So how can I unmute Yin Chuan Yu? Yeah, he has raised the hand. Sorry for the technical problems.
Oh, he should unmute himself.
Ah, okay. Yeah, Yin Chuan, you can talk. Yeah, please unmute yourself. I try to do it myself, but somehow I'm not able to. So I have a suggestion. While Yin Chuan Yu is trying to unmute himself, I ask a question. So Kirsten, so your talk revolved around these higher order spin interactions. So how can one understand them microscopically? So I thought microscopically all these spin interactions are always binary. So magnetic dipole interaction and so on. So how can one understand these higher order spin interactions microscopically?
Well, usually the first order interactions, the pairwise, they are usually the leading term. And then the ones where the electron hops around more than two sides, they don't contribute so much to the total energy in order to change the ground state, for example, in ferromagnets. But once you have competing energies, they can play the decisive role. So they just come out of the Hubbard model as higher order. And yes, usually you can neglect them, but apparently not always, and they can be used to generate very interesting spin textures on the atomic scale.
Thank you. So how is it actually with frustrated systems? So in frustrated systems, it's usually argued that all these interactions are frustrated. But now when these higher order interactions come into play, which I have not been aware too much up to now, I mean, don't you break then the degeneracy of the ground state?
Yes, in this I mean, in the very simple Heisenberg model, this rowwise antiferromagnetic state and the superposition state, they are degenerate. So they should coexist. For example, if you have different islands, once you find this state and then you find the other state. But basically, you can't really have a real material where these higher order interactions are zero. So that's why one of them will be the ground state, depending on the sign of the higher order interactions.
Okay, thank you. So I still haven't heard anything of the Yin Chuan with the raised hand. Also, I didn't see him asking in the chat. Well, yeah, so then a final technical question to you, Kirsten. So I was very much impressed by your technique. So how do you actually prepare your spin polarized tip? Because it's also in an environment with quite high magnetic fields. I saw something like more than 1 Tesla. How do you get this spin polarized tip? And how can you control its magnetic moment? Is this possible?
So when we look at these nanoscale magnetic states, often we use a chromium bulk tip. So we use an antiferromagnetic material as chromium, and that's just what we use as a tip. And because of the exponential dependence of the tunnel current, we will always have one last chromium atom that will determine the spin polarization of the tunnel current. And then if we apply an external magnetic field, we don't expect the chromium tip to change. If we need to have a tip that changes the magnetization direction in external magnetic field, then we, for example, use a very thin iron-coated film. So all our STMs are designed to take out the sample in situ and transport them to a heating and deposition stage and put them back into the STM. And that's how we can then have an iron-coated tip, which we can control by external magnetic fields.
Thank you very much. Yeah, so it's a very impressive technology. We have now a question in the question and answer section. So Kirsten, you can either click on it and read it yourself, or I can read it for you as you like.
I will read it so everybody can hear it. Right?
Okay.
Based on the results so far, do you think there are more new interaction terms? If so, what are they? Yes, so this should actually be a question for a theoretician. And I know that a lot of theoreticians have started looking in this direction, and they actually do find different interactions. So they find chiral interactions that are related to the topology. And they only arise in non-collinear magnetic systems. Basically, they scale with the solid angle of 3 neighboring spins, and they are related to topology. So there has been a lot of work, and I know about a lot of manuscripts around the group of Professor Stefan Blügel in Jülich. So they are working on this now.
Okay, thank you very much for your answers. So it's now 37. So the next talk will be in 2 minutes or 3 minutes. So I think it's a nice point to stop here. Thank you very much again, Kirsten, for your great talk and discussion. And if there are more questions, of course, later then in the coffee room. Thank you very much again.
Thank you.